All right, as we said before, reaction mechanism is the pathway in which the reactants turn into products. If we look at a balanced equation, we don't get a clue about what these steps are. If I was to look at this, on face value, right? I mean, it's the collision theory, right? Things have to collide in order to react. So what you're basically implying here is a ninefold collision in order to react. Well, that's extremely unlikely. I mean, frankly, collision's unlikely. I mean, if you've got all these reactants winging around, a bullet has to hit a bullet essentially, right, in order for the reaction to occur. So anytime you have multiple things that have to slam together simultaneously, well, that's really going to slow the reaction up. So a bullet hitting a bullet would be a second order kinetic relationship. Three bullets hitting each other would be a third order kinetic relationship. So a reaction mechanism is a description of how the reaction occurs. Again, it's the collision theory, so things have to collide in order to react. So it's expressed as a series of equations. Each equation is called an elementary step. And when you add the elementary steps together, you get the overall equation. So for example, if I have nitrogen monoxide react with oxygen to make nitrogen dioxide, you have to do experiments in order to figure out what the mechanism is. So during an experiment, you're fishing around in the soup that you're making here, and you come out with N2O2. Well, N2O2 isn't a reactant, N2O2 isn't a product. We can't collect activated complexes, so this is what we call an intermediate. Something that must have been made in one of the steps during the collisions, and then it was consumed in another step. So proposed mechanism to make that intermediate. An NO gets slammed by an NO so that the O's are orientated towards each other. And you get a bond between the O's. So this is where we get our N2O2 intermediate. That N2O2 intermediate in turn gets slammed by an oxygen. We break the OO connection between the N2O2 intermediate, and we go to products with two NO2s. So the way this is proposed, right, the N2O2 is made in one step and then burned in another step. So this is what an intermediate is. Made in one step, used in another step. Created, then smacked into, and gone, right, to create the reactants. So when I add these two steps together, the intermediate cancels out, right? It's redundant, and it's on both sides of the arrow. So it goes into the reaction and comes out, well, it comes out of the first step and then goes into the second step. All right, so elementary steps can be unimolecular, involving one molecule, bimolecular, involving two molecules. Again, what we are implying here is two things colliding. Termolecular, meaning three things colliding, and so on and so on. These molecules can be the same or they can be different, right, depending on what the mechanism is. So a unimolecular step is a step where you have one thing falling apart, disintegrating essentially, and in a bimolecular step and a termolecular step, you're getting collisions. So both these steps are bimolecular, right? In the one step, we have a collision to make the intermediate. Then the intermediate gets slammed by oxygen to go to products. So two bimolecular steps in this mechanism. All right, rate laws and elementary steps. All right, for a rate law, the overall reaction cannot be determined. The rate law for an overall reaction is determined by experiment. It cannot be deduced from looking at the equation. That's not so for an elementary step. I can look at the elementary step, the equation for the elementary step, and I know what's smacking into what. All right, so it's a unimolecular step. It's going to follow first order kinetics. It's going to be dependent on the concentration of the thing falling apart. If it's a bimolecular step, it's going to have two things smacking into each other, so it's going to follow second order kinetics. Doubling both of them would quadruple the opportunity for collisions, and so on. All right, so as far as how fast the reaction is going to go, a reaction can only go as fast as the slowest step. So if you have a three-step mechanism, the slowest step is the one that's determining how fast the reaction is going. It can't go any faster than that step. So that's called the rate determining step. All right, so when you're writing a mechanism, it has to satisfy two requirements. First, when you add up the elementary steps, things that get made in one step and used in another have to cancel, so that when you add the steps together, you come out with the balanced equation. The second requirement is that the rate law for the rate determining step has to agree with the experimentally determined rate law. So, for example, I can't think of synthesis, decomposition. The decomposition of hydrogen peroxide into water and oxygen. This is facilitated by iodide. Iodide in this case is going to be what we call a catalyst, and we'll talk about them later. But for right now, first with respect to iodide, not iodine, and first with respect to hydrogen peroxide. So this is what it was experimentally determined. Increase in the concentration of the iodide doubles the rate of reaction, doubling the concentration of the hydrogen peroxide doubles the rate of reaction. Double both the catalyst and the hydrogen peroxide, you get a quadrupling effect. So step one, you could have iodide slamming into hydrogen peroxide to form water and IO minus. Now IO minus isn't a reactant, IO minus isn't a product. It's something that was made in one step, then that gets slammed in the next step. So IO minus then gets slammed by hydrogen peroxide to form water, oxygen, and iodide. So IO minus was made in one step, used in the other step. That makes it an intermediate. So when I add these together, they cancel. Iodide went into the reaction the same way it came out. So went in as a reactant, came out as a product. So again, when you add these expressions together, iodide cancels. So I'm left with two hydrogen peroxides forming two waters and oxygen when I add the steps together. All right, so here's another example. We have nitrogen dioxide reacting with carbon monoxide to make nitrogen monoxide and carbon dioxide. Now, it was experimentally determined that if you double the concentration of nitrogen dioxide, you quadruple the rate. All right, so it's a second order relationship with respect to nitrogen dioxide and a zero order relationship with respect to carbon monoxide, meaning increasing its concentration has no effect at all. So we have to come up with a mechanism why. What slams into what in order for reactants to turn to products? So which of the two steps in the proposed mechanism is the rate determining step? All right, so we have to have a mechanism, and we have to have in the rate determining step a step where nitrogen dioxide is being slammed by nitrogen dioxide. If I look at step one, if I increase the concentration of nitrogen dioxide, meaning doubling both of those, I'd quadruple the opportunity for collision. So the first step is the slow step. The second step involves having carbon monoxide slam into the intermediate that's formed during the first step. So hey, increasing the concentration of carbon monoxide is not going to increase this rate of reaction. The reaction can only go as fast as the slow step. So carbon monoxide has no relationship to the rate of reaction, only the nitrogen dioxide. You could have a proposed mechanism where carbon monoxide slams into nitrogen dioxide to go directly to products, but it doesn't correspond to the rate law. Right? This would be the corresponding rate law if this was the case. First order with respect to carbon monoxide, first order with respect to nitrogen dioxide. Well, that's not the relationship. It was determined that it was second order with respect to nitrogen dioxide. All right, so guys, a mechanism is a theory. It can only be proven, it can only be disproven. It can never be proven correct. So mechanisms are constantly being refined. As soon as you find a new intermediate, you have to redo the proposed mechanism. So experiments can eliminate proposed mechanisms from consideration, right? So if all of a sudden you find a new intermediate or something while you're doing the experiment, you have to come up with a reason why this intermediate is showing up.